Okay, let's talk about chemical quantities and reactions now. So in the chemical reaction of Fe and S, so iron and sulfur, the mass of the reactants is going to be the same as the mass of the products. Because remember, again, things can't be created or destroyed. They're just going to be transferred between states, right? So what we're going to do for this video is learn how to work with, given a quantity of moles in a reactant or a product, we're going to use a mole-to-mole factor from the balanced chemical equation to calculate the number of moles in another substance in the reaction. That's a mouthful. All right, so what did I just say? We have the law of conservation of mass, and this indicates that in an ordinary chemical reaction, matter cannot be created or destroyed. So there is no change in the total mass that's going to occur. The mass of the products is going to be equal to the mass of the reactants. So an example that we can look at here is tarnish, which is Ag2S, and this forms when silver reacts with sulfur to form silver sulfide. So if we set up our reaction over here, we can see that two silvers, right, and a sulfur is going to react to make our our tarnish. And so you can see that, again, we have to make sure that everything's balanced. So Ag2, S is S. So twice the number of silver atoms react as sulfur atoms. Okay, so you can see that there's, you have your silver here, you have your sulfur, and then when it comes together, it ends up becoming our rust, or our tarnish. Okay, and if you add this mass with that mass, we're going to end up getting that mass, because again, we cannot create or destroy, we can just transfer. So information from a balanced equation. So here's a summary of reaction types. If we have a combination, we're combining things. A plus B equals AB. If we're decomposition, we're destructing it, right? We're separating it. So it's going to be AB separating out into A plus B. If we have a single replacement, you can see that A plus BC equals AC plus B, because we're having one single replacement. And then here's an example over here too. And if we have a double displacement reaction, then we have AB plus CD, and you can see that A and D are now going to combine, and C and B are combining, so they're replacing each other. Okay, then we have combustion reaction, and then remember the delta sign is heat, right? And so this is a fun little thing to keep on hand so that we can refer back to it. So what are we going to do while we're reading these equations in mole? Let's consider the following reaction. We have 3 irons, 3 sulfurs, and we're ending up getting 1 mole of iron sulfide. So we would read this as 2 moles of Fe plus 3 moles of S is going to be 1 mole of Fe2S3. Okay, so again, I mean, it sounds very mouthful complicated, but you guys are super smart, and you can see that they just have to calculate and equate out on either side. Okay, so applying what we've learned in this chapter, we are going to write conversion factors from the equation. So a mole-to-mole factor is a ratio of the moles for any two substances in an equation. So for instance, we have 2 irons, 3 sulfurs to give us 1 Fe2S3. So how would we write this up? We have 2 moles of Fe over 3 moles of sulfur. Remember, it's the same if it's flip-flopped, okay? And then the same thing, 2 moles of Fe over 1 mole of Fe2S3, same, you can flip-flop it. So it's just showing you that you can write it either way, and it's the same thing. It just depends on what you need to cancel out. So let's consider the following equation. If we have 3H2 in the gaseous form plus N2 in the gas form, and that's going to end up giving us 2 NH3s in the gas form. Let's figure out. For question A, what's the mole-to-mole factor for H2 and N2? And for B, what's the mole-to-mole factor in NH3 and H2? Okay, pause me, work on it, come back. So for question A, the mole to mole factor for H2 and N2 is 1 mole of nitrogen is 3 moles of H2, because we have 1 mole of nitrogen here to 3 moles of H2. So then what's the mole to mole factor for NH3 and H2? Well, if we have 2 moles of NH3 here and here, that's going to be the same as 3 moles of H2, because remember, they have to balance each other out. Okay, so that would be our mole to mole factor. So how do we do calculations with these guys? Well, let's practice. How many moles of Fe2O3 can form from 6 moles of oxygen? Let's set it up. We have 4 Fe in the solid form, 3 O2 in the gas form, and that converts into 2 Fe2O3 in the solid form. So what do we have? We have the relationship of 3 moles of oxygen right here is going to equate to 2 moles of Fe2O3. So let's use that mole to mole factor to determine the moles of Fe2O3. So we have 6 moles of O2, okay, times, because we were just asked for the 6 moles of O2 right here, so that's where that 6 comes from, times by the conversion factor of 2 moles Fe2O3 over 3 moles of oxygen. We want the 3 moles of oxygen to cancel each other out, so we have 6 times 2 divided by 3, and that ends up giving you 4 moles of Fe2O3. Okay, so what is our handy dandy little guide? Well, we are going to state the needed and the given quantities in either moles or grams. Then we're going to write the plan to convert the given to the needed quantity. And then we're going to use those coefficients to write the mole to mole factors, writing the mole mass factors if they are needed, and then set up the problem to give the needed quantity. So let's try.